Good afternoon, everyone. My name is Muhammad Saeed, and I am PhD student at the University of New Mexico, Department of Civil Engineering. And I'm working in research group of Dr. Hojati. Today, I'm going to present part of my PhD research that is related to additive manufacturing of engineered cementitious composites. This will be the outline of the presentation. There are too much detail, but I will try to finish briefly in 20 minutes. So the 3D printing of concrete is gaining the attention of researchers and the industrialists because of its different potential advantages, such as the totally automatic construction. The cost is low in terms because it doesn't require any labor force, and also the former cost can be saved. And the material wastage is also very low as compared with the conventional concrete construction practices. On the other hand, the safety concerns are not very serious if we compare with the conventional concrete practice, and the efficiency of construction is very high. And we can build the structure within the days that could take months using the conventional construction process. This technology is gaining the ground exponentially over different years as an alternative of the conventional approaches because of its at the projects where the automation could be very cost effective, and due to the geometric restraints, it is very difficult to cast the complex geometry at large scale in the conventional concrete practices. But its adoption is still very slow because there are no existing standard and codes exist so far. And there are a lot of challenges that need to be investigated to apply it at large scale. But still, this technology has been applied in the transportation infrastructure application, in the bridge, especially in the bridges. A bridge for cyclists is constructed by 3D printed concrete in the Netherlands. Another bridge for the pedestrian is with the span length of 86 feet in Shanghai. And the world's largest 3D printed bridge of 95 feet span is under construction in Netherlands. Part of its different potential advantages, there are so many challenges involved to apply it at large scale. And there are different factors that affect the printing quality and other parameters. And Murcia et al. Suggested a tetrahedral model to understand all these variables. And most important of them is the rheology and grain strength, that is the fresh property of the 3D printed concrete. Rheology is basically study of the deformation of material in fresh state. So the challenges involved are to achieve a mixed design that has sufficient rheology and grain strength. So if we can get a mixed design with enough rheology and grain strength, we can solve the other problems somehow, like the printing quality and other variables. And all the properties are basically connected to the rheology and grain strength. Another big challenge is the reinforcement. Several different researchers have used several approaches in the 3D printed construction, including the pre-install reinforcement, post-install reinforcement, and in-process reinforcement layers. And some of them have also used the short fiber to reinforce the 3D printed concrete. But still, none of them is quite effective because using all these approaches, the automation involved in the 3D printing is disturbed because we have to stop the printing process, and it can slow down the printing process also. And to lay down these reinforcing mesh, we need the labor force also. And we claim that we don't need labor force in 3D printed concrete. So to address the issue of the reinforcement, engineered cementitious composite, which is the class of ultra high performance concrete, could be a alternative to minimize the required of reinforcing bars to some extent, because this ECC has potential of providing high tensile liquidity, tight crack width, and it has high strength both in tension and compression, and durability is also very good. So we come up with the experimental work and design the ECC mixes, 4 different ECC mixes by utilizing the supplementary cementitious material such as fly ash, slag, silica fume, and metacooling. And the fiber used was the 1.5% of the total volume, and we use polyvinyl alcohol fiber, PVA fiber. This was the mixing sequence, consists of 3 different stages. The dry material was first mixed for the 10 minutes at low RPM, and then after 10 minutes, the solution of water and superplicizer were added, and mixing was continued for 5 more minutes. And in the last stage, the PVA fiber was added, and mixing was done at 5 minutes, followed by a 5-minute mixing at high RPM. And after the rheology trial was done, and the printability was assessed in terms of suitability and buildability. This was the printing system we used, a gantry system with 3 degrees of freedom, and the print area of 2 by 2 by 2 meters. So the initial trial we done on printing trial on these ECC mixes, we faced so many challenges because the printing of ECC has different challenges, like due to high content of fiber, it can block the printing nozzle, and fiber dispersion in the mix is another issue. And we get very poor quality in terms of suitability. As you can see, the printed filament doesn't have a good dimension consistency, conformity, and the surface quality is also not good. If we see the buildability and shape retention, most of the mixes was collapsed after printing few filaments. So to address this challenge, to fix this printing quality, we use the viscosity modifying admixture, that is methyl cellulose, which yielded 4 more ECC mixes. And the experimental program was consist of, because the fresh property, especially the rheology, has is of very importance to get a printable 3D printed concrete. To consider this, we assessed the flowability by using flow table, and rheology was measured by using rheometer, Brooksville rheometer, and the rheology evolution over time was assessed for 0, 15, 30, 45, and 60 minutes. A hysteresis loop technique was used, and when we apply the shear rate, the material response, that is static yield stress, dynamic yield stress, positive viscosity, and physiotropy was measured, considering the material as a Bingham material. The extrudability was assessed by printing a hollow scale of 60 by 60 centimeter, and the dimension such as width and thickness are measured at 5 different locations of the filaments to assess the dimension conformity and consistency. The buildability was assessed. We printed a 60 by 10 centimeter wall, and the deformation of bottom layer was monitored with respect to printing each layer on top of it. And at the end, the dimension of the wall was compared with the design dimension. The flow table results show that the mixes with the addition of viscosity modifying admixtures have significantly low flowability, because the methyl cellulose has a potential of water retention that leads to low flowability, and we need to adjust the water binder ratio of these mixes to make them printable. The rheology results shows that our evolution of time from 0 to 60 minutes, the plastic viscosity was show the increasing trend, and similar pattern were observed in case of the static yield stress. And if we compare the standard ACC mix with the methyl cellulose enriched mixes, with the addition of the methyl cellulose, the rheology property was significantly improved in terms of the plastic viscosity and static yield stress. So the static yield stress is actually the maximum stress required to break the material from the solid state to the liquid state. A similar pattern was observed in case of dynamic yield stress and thixotropy. Thixotropy is very important property when we are dealing with 3D printing of the cementitious material. So it is actually the structural recovery of the material with respect to time at the rest. So the thixotropy was significantly increased. And this could be attributed to the potential of methyl cellulose because it has water retention capacity. It has potential to increase the plastic viscosity and the thixotropy. Similarly, the methyl cellulose particles can adsorb on the particle of cement and bridge these particles. And this phenomena can lead to the modification of the static yield stress. The printability trials show that extrudability of the mixes when we compare the methyl cellulose enriched mixes with the standard ACC mixes. The mixes with the addition of viscosity modifier mixtures show a less variability if we compare the dimension of filament with the design dimension in terms of width and the thickness of the mixes. This is clear here. And we also investigate the effect of printing speed. What is the effect of printing speed if we increase it from 1 centimeter per second to 5 centimeters per second on the extrudability of the printed filament? So we can see that if we increase the printing speed, the dimension of the printed filament kept decreasing in terms of width and thickness. And similarly, the water simmer ratio, water binder ratio also have effect on the printing quality. And you can see the dimension, conformity, and consistency, and the surface property of the filament was significantly improved with the addition of viscosity modifying admixtures. A similar pattern was observed for another mix, that is FF14 SF10. And with the increment of the printing speed from 1 centimeter to 5 centimeters, we observe a similar pattern, the reduction of the printing parameters. To evaluate the buildability, we consider two time gap between the printing layers, 0 minutes and 5 minutes. So the printing time gap means we printed one filament and then we waited for the 5 minutes, and the second filament was printed after 5 minutes. So at 0 minute time gap, the standard ACC mix without any addition of admixtures will either collapse after printing the 5 layers. And if we compare the same mix with the addition of MC, you can see the difference in printing quality, and the mix was buildable enough even at 0 minute time gap. But the standard ACC mix the buildability was good at 5 minute time gap. Similarly, if we see another mix with the addition of slag at 0 minute time gap, the buildability was good, but the printing quality you see is not satisfying. And if we compare the similar mix with the addition of MC, the buildability was significantly improved and the printing quality is also very good. And at 5 minute time gap, due to more time gap between the filament, this mix was stiff enough that it was not extrudable anymore after printing the 6 filaments. But if we compare with the addition of MC, the same mix was flowable enough that it could be printed even after the 5 minutes time gap. At this point, we can conclude another thing, that the mix design also has a significant effect on the printing quality. If we compare the standard ACC mix that has fly ash and with the mix that has slag, you can see the difference in printing quality, that mixed ingredients also affect the printing quality of the filament. Although the time gap improved the buildability, but if we see in terms of the interlayer bond strength, you see at the 0 minute time gap, the bond between the filament was good and there was less porosity. But when the time gap was 5 minutes, you can see a gap between the filament, which shows that the interlayer bond between the filaments is somehow reduced and the porosity is also increased. In the end, we can conclude that the flowability of ECC enriched mix was significantly reduced because of the water retention capacity of the tile cellulose, and the rheology was improved over the time. If we see the rheological parameters such as plastic viscosity, yield stress, and the thesotropy of the methyl cellulose enriched ECC mixes. The printing trial shows that the storability and buildability and also the shape retention. If we compare to the standard ACC mix, the mixes with addition of methyl cellulose has very superior printing quality. And when we evaluated the effect of printing speed, we increased the printing speed from 1 centimeter to 5 centimeters. The width and thickness of the printing filament kept decreasing as we increased the printing speed. But at 5 minute time gap, when you introduce the time gap between the printing layers, it could be 5 minutes, could be more, but the buildability was improved, but the interlayer bond strength between the filament was quite weak and the porosity was also increased. That could affect the mechanical performance of the filaments. In the end, we can conclude that the methyl cellulose could be effective admixtures to tailor the rheology and to modify the printability of 3D printed ECC mixes. The next phase of this work is to assess the mechanical performance of similar ECC mixes. We are done with the printing quality. We fixed the printing quality somehow. Now we are going to assess the compressive strength of both 3D printed specimen and cast specimen. To assess the flagellate strength, 3D printed beams was printed by using these mixes. And for assessment of direct tensile strength, our dog bone specimen was used to assess the direct tensile strength. In the end, I want to thank the Transat to fund this project and other vendors to provide us the material used in this project. Thank you, and I am open for the questions.